Today we are very happy to have Simon Knapen from LBL. He will tell us about the dark matter scaling in low threshold detector. Take it away.
All right, thanks. Thanks so much for having me. So this is, as we already pointed out, work with Tongyan and Jonathan, who used to be Tongyan's postdoc, and then some students of Tongyan's at San Diego. Okay, so I think for this audience, I don't have to go over the usual rotation curves and all that stuff. We are probably on the same page that dark matter is the kind of thing that we think exists in the universe. Here's sort of so usually people plot this sort of one-dimensional axis of like where the dark matter can live and so forth. So I made an attempt here without being quantitative, obviously, at also drawing the strength of the dark matter coupled to the standard model. And so unsurprisingly, if you go very low masses, the constraints on how strongly it can couple to the standard model become more and more strong because of astrophysics and precision experiments. So this is like, you can have force experiments and so forth, torsion balances, or you can just start boiling off dark matter from stars, which kills the star, and so you can settle in it. You go a bit higher in mass, you have meson factories, like most of them are in Bell, and then the sort of highest scales of sort of terrestrial experiments that are not direct detection that we're looking at the LHC, where you can try to make it directly. So I tried to put some of the sort of classic models on here as well. You can argue exactly where these blobs are supposed to be. And so the two...
So what's the boundary between small and very small in the coupling? Typically...
You're looking at, it depends on whether you couple to electrons or to nuclei.
Yeah.
If you couple to electrons, like you're thinking about a dimensionless coupling of 10 to the minus 15.
10 to the minus 15, okay. That is considered very small.
Nuclei, something like 10 to the minus 12 to the minus 9. It depends a little bit on whether you're derivatively coupled or not and so forth. But like very, very small.
Oh.
So this is 10 to the minus 4-ish, and this would be like order 1-ish.
Okay.
And on, this would be LHC. But anyway, so since this stuff is supposedly around our hill, we built experiments to look for these things. And so the axioms on the WIMP have been the ones that we look for most aggressively, because they are the ones of all these candidates that we have the most hope I can live the highest up in this plane. And so you're probably very familiar with how these various things work. Now, in the last few 5, 10, depends how you define it, number of years, there are some a bunch more models that are here very schematically mapped out. So we know now that you can have dark matter that lives at lower masses down to roughly 1 MeV if it's in thermal contact with a standard model. Otherwise, you end up having problems with Big Bang nucleosynthesis. But if it's not in thermal contact with a standard model, like in a Friesen model, it can go down all the way roughly to this boundary here, where you run into either warm dark matter limit or a stellar cooling constraint. So this scale over here is set by, roughly speaking, the temperature of your typical white dwarf, the order of 10-ish keV or so, where you can start boiling off dark matter. That happens to coincide with a warm dark matter limit. And so what we've been trying to do for the last couple of years is try to see, can we construct experiments that we can look in this region over here, which a priori looks like it might be accessible to us. Oops, that's not me.
The cable cannot come out of
it's
the hole, maybe. It's loose.
It's happy again. Well, let's proceed. Anyway, so here's a slightly outdated but qualitatively useful plot of the dark matter direct detection landscape, so cross-section versus mass as usual. And so all these shaded things are exclusion limits, and some of the unshaded things are where we're pushing down. And so, of course, if you want to go to neutrino floor, which is this yellow thing over here, just get yourself more xenon and you wait longer. You integrate as much exposure as you can, and you try to suppress your background. It's very, very difficult, very, very slow, and a lot of effort has been done on that. And so we will eventually get to the neutrino floor. In the meanwhile, you can try to also push in this direction. And then your design driver for your experiment is very different. So now you don't need a large experiment because there's plenty of dark matter that you haven't seen, potentially, and also your cross-sections are much larger here, the unconstrained cross-sections, than what you have over here. So you're looking for a very small detector with either a very low threshold, like a colorimeter, where you can detect very small energy depositions, or you're trying to look for individual electron recoils. So you're just counting the number of electrons.
Let me just try to wiggle the thing here.
Should I wiggle it stale?
No.
Oh, so you're fine.
Let me just see. Yeah, it looks pretty loose.
Well, we'll see.
Hopefully.
Sorry. So anyway, either very low threshold calorimeters or you're looking for individual electrons. And so I'll tell you a little bit about some experiments that are going to look in this direction, and then I'll tell you about what we need on the theory side in order to make sure these things are successful.
So before going on, can I go? Okay. So is there any experiment really trying to measure the neutrino floor?
Yeah, so these guys will eventually start nibbling on the neutrino floor. And so the latest snow models, they have rebranded the neutrino floor as the neutrino fog.
Yeah.
Right, because like they're like starting to push in there, and they want to make the argument that maybe if they can collect enough statistics, maybe they can still look for dark matter there, if they can try to understand the neutrino floor and so forth. But, so yeah, so the super large things like Darwin, for instance.
Okay.
If they get built, because they're very expensive, like you need order 1 fraction of the world's xenon, then they would get there.
Okay.
If you want to look for the neutrino floor over here, of course, it's much easier. But the neutrino floor is not inherently interesting, right? I mean, it's just solar neutrinos. We've seen these things before.
But this is coherent neutrino scattering, right?
Yeah, coherent neutrino scattering, well, you do that at a reactor usually.
Okay.
Yeah, so it's already seen in a reactor.
Sure.
So yeah, it's more of a nuisance than like a physics opportunity, unfortunately, as far as I'm aware.
Okay.
Unless it's for some reason not there, then okay.
Yeah, then you.
really weird. But that's not likely. Okay, so this is sort of the diagram that people show often about how modern day operating dark matter detectors work. So you either collect charge, heat, or light usually being scintillation light, or you try to do 2 out of those 3 such that you can have better discrimination with backgrounds. And so this is a bunch of experiments here that are doing this. So all 3 of these are useful for the next generation experiments. So for what we're going to be talking about today, I'm going to be talking mostly about charge and heat. However, some of the materials we're talking about, so for instance, gallium arsenide, are scintillators, and they can also be used to collect light. But there is just not a ton at the moment that needs to be added on the theory side. So I'm going to be focusing on those 2 a bit more. So a good example to start with, because it really explains how these new detectors will work, is super CDMS. So this is roughly what it looks like. So this thing is going to be, it's being commissioned now. You're thinking a hockey puck, it's like this big. This is they have germanium versions and silicon versions. And so these little rails over here that you're seeing on the top are superconducting collection fins. And so what they're used for is the following. So dark matter comes in. It creates a bunch of phonons. And so this crystal is at cryogenic temperature, so about something like 40 millikelvin. So this thing is extremely cold. There's no phonons at all in this crystal. And the phonons that are made by the dark matter or whatever nuclear recoil you have, they can travel ballistically, bounce around in this thing off the walls until they hit one of these superconducting fins. And then they create quasiparticles. So they break up Cooper pairs. That energy is then drifted to like a really tiny superconducting film, which is called a transition edge sensor. So you're tuning the superconducting film onto its critical temperature. And if it gets a little bit of energy, it goes non-critical, and that's how you measure the amount of energy that this big detector has deposited into phonons. So the idea is like you need, in order to have a good thermometer, you need something with a really small heat capacity, so very, very small volume, and you need to try to interface that with like a large chunk of stuff, because otherwise you don't see enough dark matter events, basically. And so this is how they do this.
So you got to set this thing up so that the dominant way these phonons lose energy is, or at least a significant fraction of their energy is not lost through, I don't know, escaping through the sides or
Correct.
whatever.
Yes.
Right?
Yeah, that's right. And so that determines what fraction of the surface you have to cover with these collection fins. So these guys have a phonon collection efficiency above 90%. So this works very, very well. These phonons just bounce off the walls of this crystal very well, unless they hit one of these fins and then they get absorbed. So this is demonstrated to work really nicely. The other thing they can do is they can put a bias voltage onto this thing. You put like a kilovolt worth of electric field on this. And then maybe you'll make some electrons if you have a hard enough collision. These things get drifted upwards. And when they do, they create a bunch of phonons in the crystal as well. Just because there's drag, basically, right? So they lose energy to heat. And those phonons again get collected, and you get like a delayed signal of this electron drift. You can measure how many electrons were being produced by calibrating how much heat you saw after the original flow on peak, basically. And that's called the WIMP model. But okay. So that's how Super CDMS works. And so the future version of this is something called SPICE, and so this is being developed at Berkeley by Matt Pyle's group. And so what they're doing here is, first of all, they're building a much better sensor, so they're making it smaller, so it has a lower energy threshold. So that's this purple thing over here. These blue things are these collection fins. They look a little bit different geometrically from Super CDMS. And they also shrink down the crystal a lot. So this is like a centimeter by a centimeter by a centimeter cube. And now you no longer put a bias voltage. So what happens in a bit more detail is very similar to Super CDMS. You have a phonon that comes in. In reality, your dark matter might now be so soft that it makes just an individual phonon. This thing tends to decay to a bunch of softer phonons. All these things bounce around, eventually get collected, and you read this thing.
So those things are still on the surface, the detectors?
Oh yeah, so this detector does not yet exist. So what does exist are these things exist, and these fins exist, and so they seem to work. They're trying to get rid of some RF power now, so they're trying to shield their device better from RF power that's still leaking in. And then eventually they're going to stick that onto a piece of material, and at that point they can do a dark matter run. But so at the moment they're doing R&Ds for the sensors. For the ultimate sensitivity, here you see a detector which is sort of a precursor of the ultimate low threshold detector. This is a slab of sapphire. It's about this big, and it has an energy resolution of about 4 eV. So this is already way lower than Super CDMS. It works in the exact same way as this one. And each of these dots over here are basically an array of sensors like this. So they already have something that works. They're doing a dark matter search with this thing now, which will set some nice limits. This one will ultimately have an energy threshold of about 10 millieV. So you can sense an individual phone, basically, which is something that's never been done before.
Why is the threshold at CDMS worse than 4 eV? I would have thought that's, a typical ionization energy. That should be I would have naively thought that's a pretty high energy scale for them.
Well, they're not. There are two things, right? So their sensors are not, again, the energy resolution, which is, the energy threshold is proportional to the energy resolution. So that is proportional to the heat capacity or the volume of this sensor over here. So what these guys are doing, they're trying to build smaller and smaller films so they can get better and better energy resolution.
So it's more the total energy. I could think of that threshold as a threshold on the total energy.
That's right. Yes.
Not on the end. It's not some threshold to get particles to be produced. It's
correct.
I need a total amount of energy that's big enough that my sensors can.
Now, as we'll see in a second, Super CDMS is, because of this bias voltage, they can get thresholds of the order of a few eV already on the electron recoils, but only on the electron recoils. So there's always a different energy threshold depending on whether you're nuclear recoils or electron recoils. The nuclear recoils are usually lagging behind because it's much more difficult. Because you don't have this natural amplification mechanism by putting an electric field over it.
Why does this have to be a polar crystal?
I will explain that later. Okay. Yeah, we'll get there. Yes, this is very important, but for physics reasons, that will involve theory. This is another thing that they're doing in Berkeley, which is sort of the analog, if you want, the futuristic analog of the liquid xenon detectors. But the idea is to use liquid helium because helium is a much lighter atom. And so if you have a light dark matter colliding with it, you can extract more kinetic energy than if you have this massive amount of this massive xenon atom, basically. And so these guys are trying to do is, again, this thing is a superfluid. So you're creating some phonons that bounce around off the walls. Either you detect them on the walls, so you build some sensors here, or you try to get them to hit the surface where they evaporate a helium atom, and then this helium atom can drift up to this sensor over here, where you can try to see this atom sticking to your little superconducting sensor. That's a nice thing to do because it costs you about a millieV worth of energy to evaporate a helium atom from the surface. Because helium doesn't like to bind to itself very much. It has like a really, really weak, a very small evaporation energy, because it wants to be a gas, right? But then once it sticks to this material over here, there's a van der Waals binding energy that gives you a couple tens of millieV. So there's a natural amplification of the energy once you're trying to detect this thing. And so we're trying to use that to their advantage. This is a very complicated experiment as well, but they should be really good for like low energy nuclear recoils. And finally, there's a couple different experiments that are looking for electrons. Electron excitations. I already mentioned super CDMS, which is like different technology. This thing is called Sensei. So Ruben Essig and Tomer Volensky are sort of the folks who've been really deeply involved in this in Tianjin. And so what this is essentially a really super fancy CCD camera. So normally with a CCD camera you have a very short exposure, and so you just measure the charge somewhat approximately. What they're doing here is an extremely long exposure CCD camera effectively. So they're measuring the same pixel over and over and over and over again for several hours until they get this absolutely exquisite charge resolution, what we're seeing over here. So they can really distinguish like whether there was 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, which is very, very cool. This thing has taken some data already with about 50 gram exposure in Fermilab in the Minas cavern, and so they have the worth leading limits now on electron recoils. So all these things this one exists, and the others are in construction. Well, they're in R&D phase basically. Okay, so this is some sense of where I think this experimental landscape is going to go. And so what do we need on the theory side in order to make this useful endeavor for those folks? So we need to do 3 things. We need to think a bit more carefully about models because your usual effective field theory operators that we write down for nuclear recoils, the scales of your EFT are too low for this to be a useful approach in this context over here. So what you need to do is you need to build a full model and then analyze its constraints and making sure that you have a set of benchmark models that people can look for. So that's being done. There are rate calculations which are very interesting and important because you have collective effects in the materials that need to be accounted for, as I'll show in a second. And then finally, this is something we're starting to get into, is doing detailed background calculations. Because the backgrounds are very different in these experiments than in the ones up there, where you're mostly worried about radioactivity. So here is maybe the most important slide in some sense. Why do we care about doing detailed rate calculations? So here you see the dark matter mass on this axis from a KUV to, let's say, the Planck scale. And so the way you're interacting with your crystal or your material is always going to be proportional to the Debroglie wavelength, basically. Or this is momentum transfer. This mu is the reduced mass, and v is the dark matter velocity, which is 10⁻³ in natural units. And so that means that anywhere between the GeV and the Planck mass or something, you end up with a typical momentum transfer of the order of 100 MeV to an MeV, which corresponds to like the typical wavelength that you see in nuclei. So you just have individual nuclear recoil, nothing very fancy is going on. Got to do some nuclear physics to match your dark matter model to couple it to nuclei, but that problem has been solved many years ago, so that's understood. If you're going down from a GeV to an MeV, now your momentum transfer is much smaller, and your typical Debroglie wavelength is 10 angstrom to 10⁻² angstrom. And so you start to be sensitive to multiple atoms, or in particular the electronic structure, or the band structure of the crystal that you're scattering with. So you can't just scatter over an individual electron, that doesn't make a lot of sense. Or at the very least, you need to take its wave functions into account very carefully. And then finally, if you go even lower in dark matter mass, all the way down to the warm dark matter limit, now your wavelength is very, very long, and you can scatter with thousands of atoms all at once. So your nuclear recoil approximation definitely is no longer valid. You need to effectively integrate out the nuclei, transition to a new effective theory where you have a coupling of the dark matter directly to the phonons, and then you can use quantum mechanics as usual to calculate scattering rates. And so those are the 2 things that we've been working on to like develop these EFTs and then calculate the rates to predict the dark matter scattering signatures. So I'm going to talk about both of these, but I'm going to start with phonons, and then we'll do electrons towards the end of the talk. So here's, I'm going to try to address John's question in a few slides. So we're mostly interested in polar materials. And so let me tell you what a polar material is. It's very simple. It's basically a material which each unit cell has at least 2 different atoms in it, right? So for instance, you see gallium arsenide is the simplest possible polar material. This is this cubic thing over here is a unit cell. So you have one gallium atom, and then one arsenic atom over here in this unit cell, and this thing gets periodically repeated. Sapphire is a more complicated beast. So this has 10 atoms in the unit cell, and so the unit cell here is a little harder to see. There's a better image later. So you have 4 aluminum atoms like this, and then 1, 2, 3, 1, 2, 3, 6 oxygen atoms attached to this aluminum as a crown. What's cool about sapphire, as we'll see, is that it has a primary crystal axis. This thing is more isotropic. This thing has a primary axis. And so that's going to mean that the dark matter scattering rate with this thing is going to depend on the angle of the dark matter with this crystal axis. And that's going to be cool because we could do daily modulations for that. Now, so how do we deal, how does this phonon effective theory works? So it's actually very simple. So you just have, this is like a 2-dimensional cartoon of gallium arsenide lattice. And so you have a bunch of atoms that sit in equilibrium positions, and you can perturb around your equilibrium position, basically. And so in a real crystal, these things are connected with what we call springs, right? So they're just electromagnetic forces. And so you end up having a very large, complicated system of spring constants, basically, if you take this to leading order in Hooke's law. And you're going to diagonalize the bejesus out of this thing, and then you get the eigenfrequencies and the eigenmodes of this crystal. And this is how you do that. So you run code, of course. So there is like, this is a problem that's very well understood to high numerical accuracy in quantum matter physics. This is done with a tool called density functional theory, which is sort of loosely speaking the equivalent of numerical quantum field theory. It's the analog of lattice QCD, I guess, for quantum matter physics. So that thing gives you these force constants, you diagonalize these things, and then you get a bunch of eigenfrequencies. So this one is the easiest to understand. This is gallium arsenide. Gamma is the origin of the Briois zone, so this is 0 momentum. And if I go out on this axis, I'm gradually increasing the momentum. And so this just traces out a path through the first Briois zone of my material. And this is just the energy. So you see you have a couple acoustic modes, 2 transverse modes, 1 longitudinal acoustic mode, and 2 transverse optical, and 1 longitudinal optical mode. So 6 in total because we have two atoms in the unit cell. So the acoustic modes are where you move in phase. The optical modes is where the atoms are moving out of phase. And I have some animations in a second to make that more clear. For sapphire, things are very complicated. So again, you have 3 acoustic modes, and now there's 27 optical modes. So the only ones that are not gapped are the acoustic ones. Because you can think of them as the gold stones of the translation invariance as being broken by the presence of this crystal. And so what we're going to be doing is we're going to try to calculate the coupling of the dark matter to these individual phonon modes, and then do an EFT expansion of these things. And so loosely speaking, the EFT expansion is going to be organized in terms of the momentum transfer Q. So there's the amount of momentum that's transferred from the dark matter into the nuclei in the crystal, or into the material as a whole. So if I had a nuclear recoil, so if the momentum transfer is very high, this is just a dispersion relation because this nucleus over here needs to be on shell, so I need to have the right amount of kinetic energy. The phonon regime is going to be the regime where the momentum is very small compared to this geometric mean, of course. And this is what we're going to be expanding in. This is our expansion parameter. And it's a little analogous to current perturbation theory, although there are some important caveats that make that not fully valid analogy. But like roughly speaking, we can think about it that way. So to leading order, if you have very low momentum, so very low dark matter mass, what you're going to be doing is you're going to just produce an individual single phonon. And which phonon you're going to be producing depends on which dark matter model that you're going to be looking at. And how it's going to scale with momentum is also going to be dependent on the mode as well as on the dark matter model in question. And so this is a matching that we figured out a few years ago. And so for instance, it turns out that these higher optical modes over here, they tend to be very useful. And this is now where I hopefully can start addressing John's question. So let me explain very briefly how you go about doing this sort of matching. Oh, sorry. I just wanted to show you what one of these optical modes look like. So this is the highest energy optical mode. So the two aluminum atoms are moving in one direction and the oxygen atoms move in antiphase. And so what will happen in this crystal, this is why the polar crystal, is these things have a slightly different effective electric charge. So this one has a positive charge and these have a negative charge because the way the electrons arrange themselves in this cell. And so if it oscillates like this, it's effectively a dipole antenna that we can excite. And so that's how we're going to interact with these modes when we have a dark matter model. Here's like a reach plot just showing that if you had a kilogram a year of this stuff, which is a lot, so probably we'll never get this deep, but many orders of magnitude. So in order to reach this Tier prediction for freezing, you'd need about 1 gram of detector for like 1 month, something along those lines. So it's very, very small stuff. So this is with a dark photomediator. So you have dark matter that's effectively really charged, and so it carries a tiny electric charge, and that's how it's going to interact. And this is a freezing line for that particular model. So let's elaborate a little bit on how this actually works, and maybe answering John's question. So this is like a cartoon again of my cell. I have negative, positive atoms. If there's some external electric field, these things are going to start oscillating in antiphase because they just get pulled in opposite directions. And so this is exciting effectively an oscillating dipole. Since they're moving in antiphase, these are the optical modes that are being excited. So they store energy even if they're not propagating because they're just standing waves basically. And so the way that's done in a crystal in a bit more detail, here you see this is the Hamiltonian of a test charge E prime interacting with a dipole P just from regular E&M. It's exactly the same in the crystal, it's just a bit more complicated in the sense that there are a bunch of lattice parameters, lattice vectors, so you need to basically, this is the effective charge of a particular atom, and this is the polarization vector of a particular phonon mode. So this times this is the analog of this polarization vector over here. You're in a dielectric, so there's a dielectric constant, and then you have a creation operator to create this particular phonon mode over here, which allows you to do usual quantum mechanics with this thing. So all these frequencies, these charges, and these polarization tensors, you can get from these numerical codes that I showed you earlier. So the plots I showed you earlier were the frequencies, basically.
Sorry, why Hamiltonian is linear in terms of the creation operator?
Oh, it is because you're expanding around the origin of the potential well. So it's an approximation. It's a harmonic approximation. So you're treating this thing in the small displacement limit as a harmonic oscillator.
If a harmonic oscillator should be A dagger A, right? Why is it linear in A?
This is exciting the oscillator.
Yeah, I'm exciting the oscillator. I'm not counting the number of modes, right?
Oh, okay.
Yeah.
Okay.
But yeah, so this is, it's literally a system of coupled harmonic oscillators. The nonlinear pieces will form phonon-phonon interaction terms, and they will be important.
Okay. Okay.
Anyway, so this is great, but this only works in the limit where Q is sufficiently small. But that's not an acceptable limit for us to always work in, because we want to know something, we want to have an answer that's valid for any possible Q, because we want to go from like very light dark matter all the way until we're in the nuclear recoil regime of like, GeV or support. So if I crank up the energy of the mass of the dark matter, this is going to be an increasingly polar expansion. I need to go to higher and higher orders in Q, and eventually I need to resum the series. And so the first thing that we did is we just said, well, okay, let's calculate the next leading order piece. So now there's a diagram like this, which again comes from matching to your effective, your UV theory. You can calculate those matching coefficients. And there is this unharmonic terms over here where there are phonon-phonon interactions that also contribute. What's kind of neat is that in a very long wavelength limit, these things directly map onto the elasticity parameters of the material. So if I squeeze the material and I measure how it bounces back, I can basically find the matching coefficients for this Hamiltonian over here. But that's like a different story from a few years ago, so I will like to tell you about some of the more modern stuff. But this is what that roughly, part of what it looks like. It starts to become complicated. There's many different channels depending on the polarization of all of these things. And each of these, you have analytic formulas, but they start to become already pretty messy. It's just there's not as many symmetries as you have in a relativistic QFT, where Lorentz invariance really shrinks down your possibilities. And so this is not a sustainable way forward. So we can't compute the next leading order way in this with this sort of brute force method. That's just not really something that we can do and then also be happy with. Fortunately, there is a way forward, as I'll explain in a bit. And so we recently, with Brian and Ethan, with me and Tony, calculated this thing to arbitrary orders in the number of nuclei, the number of phonons, sorry. And then we also showed that in the limit where you take n to infinity, basically you resum the entire series, you explicitly recover the nuclear recoil, as you should, because like essentially nuclear recoil is like an infinite phonon. It's an infinite phonon. Just like QCD emerges once you start summing up Carr perturbation theory to arbitrarily high numbers, or at least it should. But here you can explicitly compute it. So in order to do that, we need to make some approximations. So first is the most important one is the incoherent approximation, and so this works as follows. So if I have a long wavelength perturbation, the interference of the phases between these guys, these different atoms can add up coherently, and it's a really important effect that gives you things like Bragg diffraction. So you get constructive, destructive interference between the different atoms. Now, if you're going higher and higher in momentum, to the extent that the wavelength becomes small compared to the interparticle spacing, the phase differences between these different atoms starts averaging out, and you can start neglecting these interference terms. And that massively simplifies your calculation. The other things that we do is we neglect unharmonic corrections beyond the leading order. So the next leading order we're not including. And if anyone wants, I can explain after the talk why we think that's okay. And finally, this is just a practical simplification. We were working the isotropic limit. So this, in principle, we can generalize, but it's just a bit more painful. So we'll get there eventually. So this is the result. So we can do this calculation. This is the answer. This is the differential cross-section of function momentum and energy. And every term, n is the number of phonons that are contributing. Every term comes suppressed by a factor of q squared, as you'd expect. And the only data that tells you about what the crystal looks like are these density of states functions for the phonons. And so you have basically a density of states for each gallium and arsenic atom here. So you see, for instance, this is the transverse acoustic peak, longitudinal acoustic peak, and a high frequency, you have the two ultimate peaks. And by just carrying out this, you can evaluate this thing numerically, and you have the answer to all orders. Now, even numerically, this thing starts to, at some point, it starts to become too computationally intensive. But you can show that in a very high momentum limit, this formula asymptotes to a Gaussian. And the width of this Gaussian is something that depends on the integral over this density of states over here. So you have a simplified form. This starts to be good around n equals like a few, 5 or 6. And then if you go even higher in momentum, this Gaussian eventually shrinks to a delta function, and you recover your regular nuclear recoil limit. So what this looks like numerically is the following. So you have, so this is, again, the differential cross-section, basically, for low momentum, intermediate momentum, and very high momentum, where we're plotting energy versus rate, basically. And the different colors indicate the number of phonons that you're exciting. So if you're scattering a very low momentum, you're just basically only exciting one phonon at a time. This one over here, and you're basically seeing the density of states helping out. So you see acoustic modes and your optical modes over here. Once you go to intermediate momentum, now the 2 phonon contribution starts mattering. There's a little of 3 phonon, and the 4 phonon starts coming in a little bit as well. Once you get to very high momentum, all of these things contribute roughly the same amount. And if you add them up, you get this dashed line over here. Well, this thicker dashed line is this approximation formula, the Gaussian approximation I showed you earlier. And so these things eventually converge to each other. If you go to even higher and higher momentum, you get more and more phonons, and this Gaussian starts to become more and more narrow. Basically becomes a delta function. So we can do this analytically and numerically. And so with that, we can project some curves. So these are not projected limits because we don't know what the backgrounds are, we don't know what the signal efficiency are going to be. But this is just, we just set some benchmark number of events per kilogram year, just sort of, we just care about the shape, not the normalization. This is a convention that people use. And so now we have a prediction for every arbitrary thresholds we can compute. How many events the experiment is supposed to see given a certain exposure and threshold. Which until this year we didn't have any prediction in this intermediate regime over here. So this is very gratifying theoretically, and I think also very essential experimentally, because they won't be at their ultimate sensitivity right away, so they'll gradually creep down, so they're going to push this way multiple versions of the experiment. So they need to know as intermediate reaches as well.
So how accurate do you think this theory is? Do you have a quantitative understanding of errors, or?
It depends a lot on where you are here and what thresholds you have. So over here, I would say at best order 1. So here it's not very good for reasons I can explain after the talk. In these sort of higher thresholds, higher regimes, and also over here, we think we're probably within uncertainties of like order 10 and 20%. So
I mean, I guess this is what condensed matter people do for a living, but you kind of would like to use this same calculation or something similar and predict things you could measure, I guess,
Yes.
right? And so, but I mean, I'm sure these density matrix things are already sort of tuned
yes.
for that, but is there anything like that that you can do? Is there some,
Yes.
are there checks that you can do, measurements to see how
Yeah,
well you're
so
doing?
this entire formulas and all these things, this is all reproduced in neutron scattering data.
Oh, okay.
So of course a different kinematic regime than what we're looking at.
Mhm.
But like the way they measure the density of states is literally by scattering neutrons, measuring these peaks, and then inferring the density of states.
Mhm.
That's how this is measured. Yeah. So yeah, there is a lot of experimental backing for these things. Here there are some theoretical subtleties that we can talk about, where you're sort of in the regime where your approximation for the dropping interference is a little dicey. So there, we have order 1 uncertainties, maybe like a factor of a few even.
Mhm.
So that there's more work needed there once we have actual experiments. But yeah, for the rest it should be satisfactory. The main thing that's missing is the directional dependence, so in the sense of the isotropic approximation is something we can try to fix, so that we can have a slightly more, we can tease out any directional dependence that's still left over that we're neglecting here. Okay, so that is phonons. One thing I didn't show you is you can make these very nice daily modulation plots, at least in the low mass regime, because of this crystal axis and the sapphire. But that work is a little bit older, so I decided to skip that and tell you about some of the electronic stuff that we've been pretty excited about lately. How much time do I have left, actually?
20 minutes.
Oh, okay.
More.
I've been talking way too fast. I'll
You know,
just-
You're at the end of your talk?
No,
You're
no,
at the end
I
of
can talk for 20 minutes. It's fine.
Okay, sure.
It's okay.
I did this once. I started ended the talk way early, and I told people that, well, I personally have never been to a talk where somebody said, that was a great talk, I just wish it was longer. So,
Well, let's see if we get to that stage.
you do you.
Okay, anyway, electrons now, right? Unless there are any more questions or comments about phonons, it sounds like we have time. Yeah.
Yeah, so when you take the incoherent approximation, are you taking the momentum of photon to be big or the momentum of dark matter?
The momentum of the dark matter, that's very important, because the momentum of the individual phonons is still small. It's just you start getting more and more of them. So your dark matter momentum is large, and that gets spread out over multiple phonons.
But don't you want the dark matter to have small momentum, so you have larger wavelengths beside the phonon?
Yeah, so the momentum transfer into the crystal, the dark matter has a relatively short Debroglie wavelength. Not short enough to have individual nuclear recoils yet, but long enough so that you can neglect the interference between neighboring atoms. That's the idea.
So the momentum transfer into the crystal is small?
Is large.
Is
Well, intermediate, depends on what you mean by, it's small compared to the nuclear recoil case, but it's large compared to the case where you make a single phonon.
Oh,
Okay.
But then the momentum of the individual phonons is still only of the order of like a couple keV each. Because a phonon can never have more momentum than the edge of the baryon isotope. It's really roughly like keV, and then that's cut off.
Okay.
Good. No, that's a good question. Any others? All right, let's do electrons. So electrons are very cool. They're very complicated. They're very underrated. The reasons are, there are 4 reasons. They're not free, they're not at rest, they're not localized, and they're definitely not alone. They feel their friends, they're polyblock, they have electrostatic repulsion. All of these things matter a lot when you're trying to do a dark matter experiment. So the first calculation like this was done by Rubin and Tomer and Tientien in 2015. And so what they did is they calculated, they used one of these DFT codes to just calculate the wave functions of the valence electrons, and then just by brute force just computed the scattering amplitudes for that. And so what you're seeing here is, again, you see the baryon isotope, so this is the momentum on this axis versus energy, and so this is the Fermi surface, essentially. So these are all the valence states, and here you have the conduction state. So you're going to try to like push an electron from here into this band over here, and then calculate what the probability is of that happening, given a certain amount of energy momentum transfer. And so that works. It's a bit painful, but it works. But like we're taking a different approach since last year, because there's an equivalent problem. Is other than just trying to just calculate these excitations, you can also ask what is the rate at which the dark matter is dissipating energy when it's passing through the crystal. And that's an equivalent calculation, but it turns out to be much, much easier. Because you can take advantage of some theorems and statistical mechanics for that. So this is I'll give you first a schematic argument, and then I'll sketch the exact derivation. So this is the Coulomb Hamiltonian, as you're used to seeing it in Fourier space, except that now I'm in a dielectric, so I put in a dielectric function, which parameterizes the response of the material, and it can be both momentum and energy and frequency dependent. And so in a sort of QFD context, you would say, well, okay, I have a propagator, I have a photon, and it's dressed exactly by this thing over here, in a sort of non-relativistic context, schematically, right? And if you want to know how much energy is dissipated by this type of propagator, what you would do is you just take the imaginary part, in other words, you slice this thing in half, and you see how much energy is lost. This object over here in compass matter length is called the energy loss function. And so it's the object that people use when they're interested in figuring out how much energy electrons, photons, and so forth lose when they're traveling through a material. So it's extremely well understood, in most regimes at least, both on the theoretical and experimental side of things. And so what we're going to try to do is we're going to try to relate this object to dark matter scattering rate, and then what we can just use the technology that's already been developed by our colleagues in compass matter length.
Sorry, this wavy line, it represents a photon or represents a photon?
Photons, sorry.
Photon.
Photons, yeah. So
Okay.
now we're going to be working at energies that are a couple electron volt each, so that's like the typical energy of the band gap. So this is like a couple EV over here. So we're at energies that are well above the typical energy of your typical phonon. So phonons show up at the order of 10 millieV.
Okay.
So they're much softer than this. So we're always going to be talking about electrons. So it's a slightly different, it's a higher energy regime.
Yeah. So basically, you only need to calculate the 2-pound photon propagator, right? That's basically what you are trying to do.
Exactly. At very low frequencies, this thing will get contributions from phonons.
Okay.
We don't need that, it turns out, because the frequencies that we're going to be interested in are going to be well above. They're basically at the order of the band gap. Otherwise, we can't excite electrons.
Okay.
So the phonon contributions are going to be negligible. But they are there in general.
So what this energy dissipation, does it go into phonons, or where does the energy go?
It goes into creating electron hole pairs mostly. And then those can recombine, and when they recombine, they create phonons, or scintillation light, depending on the material. But that recombination is parametrically slower than the original dark matter collision. So you have this factorization that's very nice. So you just need to care about how many electron hole pairs you make.
Yeah.
And then it's an experimentalist problem to figure out how they're going to see these things.
Yeah.
So
a
for
little
instance,
bit like QCD, right? So like if you make
yes,
a quark
yes,
anti-quark pair, once
exactly.
it's made, that's the rate.
Yes.
What happens next is very complicated.
There's a UV physics, infrared physics. UV physics here is EV, infrared physics is tens of millieV, and they thankfully separate. And they wouldn't. There are cases where they don't, which I can explain later. And then your light is qualitatively harder. But like in this instance, we benefit from this factorization of scales. Yes.
I mean, so electron hole pairs, I mean, you already made one of these things. Isn't that the electron hole pair, or? am I not
Yeah,
understanding
pretty
that
much,
right?
yeah, so you're pulling an electron up, and so you make an electron, you make a hole.
Oh, I see, but you're actually, yeah, but you're calculating the energy dissipation of the photon, so that's
Exactly,
exactly.
yes, it's how much energy is the photon losing.
So it's kind of like
by
computing
making
the,
electron hole pairs.
so it's kind of like more, is it sort of like computing the total rate as compared to
Yes,
some
yes.
cross-section?
Yes.
So the total rate is easier to compute.
You're computing an inclusive quantity rather
Yeah.
than a process
Okay.
by process quantity.
Got it, thank you.
Perfect, yes, that's actually, yeah, I'm gonna use that in the next talk, that's actually a very nice way of thinking about it. All right, I can, you guys wanna see how this comes about formally or like not?
I think you should decide. I
Okay,
think it's always a bad
I'll
idea
tell
to
you-
ask the audience, just do,
I'll do it. And
just
then
make an executive decision.
Okay, so the way we derive this sort of thing is as follows. Again, a little bit qualitative, but hopefully it's clear. You use something called linear response theory, which is essentially non-relativistic quantum field theory. And the object you're going to be caring about is the susceptibility, which is this chi of omega k. And so this is effectively the two-point function. This n is the number density operator of the electron at a certain wavelength. So this is the Fourier transform of the number density operator. And this is essentially just the non-relativistic retarded Green's function of the two-point function of the perturbations of the electron number density. Okay? If you know this thing, you're very powerful, you know a lot, because this tells you how the electrons are going to respond to external perturbations, to leading order in the number density. And specifically, there's something called the fluctuation dissipation theorem, which is the equivalent, the stat-mach equivalent of the optical theorem, where if you take the imaginary part of this thing, you get something that's proportional to this function S of omega k, which is called the dynamical structure factor. But more importantly, for our purposes, this is just Fermi's golden rule, right? So you see here a matrix element, an initial state, final state, summing over all these things. There's some temperature factors here that usually don't matter, and energy conservation over here, right? This is the object that you need if you want to figure out the dark matter scattering rate, because it's literally just Fermi's golden rule, that's all it is. Provided your dark matter predominantly couples to the electron number density. So this is just by time-dependent perturbation theory to leading order. And so if I can get this object over here, and I can take the imaginary part, I get all this stuff for free without having to do these matrix elements, basically. That's the idea. Now, how do you do that? So consider now the example where my perturbation is electromagnetic in nature. So there's a Coulomb Hamiltonian like this. There's an electron number density proportional to some charge, there's some external charge density that's driving my electric field. And so to leading order, you can evaluate the expectation value of the perturbation as follows. So it's going to be proportional to the external charge density, and then this susceptibility function that we saw earlier. So that's something you can compute. And then the only other thing that we need is Maxwell's equations. So this is your displacement current, and this is your actual electric field. And the difference between these things, so this is the induced charge density, is how the charge in the material is responding to the external electric field. You use this relation over here, which is the definition of the electric function. And if you put this and this together, you get this relation between the dielectric function and the susceptibility function over here. If you put that together with the stuff on the previous slide, you find that this object that you wanted, Fermi's golden rule, is proportional to the inverse dielectric function, the imaginary part of the inverse dielectric function. And again, there's some temperature factors here, which usually we're at very low temperatures, so this is usually, this term is usually 0, and then of course depends on alpha Eman in this way.
Sorry, can I
Yeah,
ask?
of course. This is
so-
very
so-
schematic,
So usually, like, if I'm just, because I'm a poor benighted quantum field theory guy, doesn't understand condensed matter, so usually when we use, the optical theorem, usually we get power by doing it the other way from what you're doing, right? In other words,
Yes.
with the imaginary part, it's just some total rate, we can calculate that, that's how we can,
Right.
and then we can even calculate loops this way. But you're doing it the other way around,
That's right.
right? And so is the point that you can treat the electromagnetic field as just a classical field, and so somehow you're doing some kind of classical response.
I have not yet told you how I'm going to calculate the dielectric
Okay,
function.
yeah, because
I'll tell it in a second.
all right,
Because
so
your
maybe I'll just
question is
let you go
justified.
on.
Like, I just rewrote the entire thing. This thing still contains
okay,
like
so
some
so far-
horrific quantum mechanics.
Okay, so this is just a
Right?
rewriting.
This
so
is just a
far.
rewriting, but I'm going to
Okay.
argue that this is a convenient rewriting, and I'll explain on the next slide why.
Okay, go to the next slide then.
I hope this is the next slide. Not yet, sorry. I'm first going to tell you what we're doing with it, and then I will explain how. Okay, now that you have this thing, you can just write down the formula for the rate, or dark matter scattering rate of electrons and whatever material you want. Dark matter velocity distribution, this depends on the dark matter model. There could be some form factor if you want. But all the material science business is packaged in this object over here, like we just argued. Right? So that's the main thing I wanted to show. And what's nice is that the screening is automatically included. So the electron screening themselves is included in this because I used this formalism. This was not the case in the calculation that Rubin and company did, where they did they just calculated wave functions. So they neglected screening, and so their result was like an order of factor of 5 or 6 too optimistic because of that.
Yeah. Basically, you're trying to say you're using full quantum theory and in the non-relativistic limit, that you can capture everything, right?
As long as you can calculate, to the extent that you can calculate what this is.
Okay,
right?
yeah.
So this is so far an exact result, but I'm going to need to make approximations. To
Okay, sure.
Could they have just calculated your ELF thing?
They could have, yeah.
They just didn't.
They did. I mean, they did the thing that any particle physicist would have done is like just calculate wave functions and evaluate the perturbation theory.
Okay.
This stuff is known by the condensed matter people from the 60s, but it's like, of course, it takes us another extra couple of years to dig that out.
Good.
I mean, they were pretty close in the end, I mean, it's pretty impressive where they got. I have to say. Anyway, this is Marcus's question, right? So, like, how do I calculate this? And so there are 3 different ways that we use, going from very simple to very sophisticated. The simplest thing is you can just pretend that this thing is just a free electron gas, and that's it. Just a free electron gas, no self-interactions, nothing, just polyblocking, and that's it. And you can calculate the dielectric function of such a thing. That's called the Linhart dielectric function. So that was done by Linhart in the 40s, and this is what it looks like. So this band over here is where you're able to create electron hole pairs, just kinematically because of polyblocking. This is a band. And then there's the plasma peak is sort of is a delta function in this model, so it's not very good in that sense.
But it means this is being hard calculated in 1940s,
Yeah, 40s, 50s.
before quantum field theory. This is quantum mechanics, right?
No, this is just statistical mechanics. It's just like you need Fermi-Dirac distribution, and then you're just perturbing electric field.
Okay, just a
It's
classical.
actually very simple. The formula is a little bit complicated, but it's not very fancy. This does not take QFT or anything.
Okay.
So there's no band gap put into this?
Yeah, so this thing doesn't have a band gap. Very good. So that means that, of course, over here it's going to be doing a horrible job. So this is a toy model. It's not very good, but it's something you can do just to compare it with the others. This is a fancier version of this, where you're saying you're doing the main thing that you're doing is you're saying, like, well, my typical material is just not a free electron gas with a single frequency. It has multiple frequencies that it could have. So I'm going to take a linear combination of formula of this ansatz and fit it to optical data. And I'm also going to allow for dissipation. So I'm going to allow for electron hole pairs to recombine and make phonons, right? And the way you do that is by just putting in a fudge parameter, like essentially a width, an imaginary part somewhere, and you're going to fit that thing also to data, right? If you do that, there's some condensed matter people who do this for a living. You get something like this, and this is called the Mermin ansatz, basically. So this is a fancier version of this, but fit to data with lots and lots. This could have like order 50 free parameters or whatever that are all fitted to optical spectra at omega at q equals 0 on this axis over here.
This is done by when? When was this done from Mermin?
These people do this now.
Now.
Yeah.
Oh, yes, okay.
Papers we're using are a few years old.
Oh, recently. Okay.
And this is the fanciest thing. This is if you do density functional theory calculation. You could also just say, okay, I'm just going to run like this code. I'm just going to calculate this on my supercomputer. It's going to take a week, but then in the end I'll have an answer. And then you can get the band gap explicitly. This particular version does a pretty poor job on the band gap. There exist versions where this is included, but like, yeah, in this one that we used it doesn't. So there's, it's basically this is the fanciest one that we have at the moment. Okay, so here are a few slices. Maybe I'll go through this a little bit faster. As a function of momentum, as a function of energy for different momenta. you see this is the plasma peak, and if you're high enough momentum, you see the electron continuum. But the main point is that, the green one does a terrible job, as you can tell, especially here. But the purple and the yellow these two methods are really nice agreement with each other.
So is it the case that that this energy loss function is just something that these different models or the density functional thing, they just compute those, and so you're using the fact that people already know how to compute that in a way? Or is that a fair statement?
Pretty much, yeah. I mean, we do have to, as I'll show in a second, not fully. Actually, let me show that on the next. Yeah, so this is all done at relatively low momentum, and so this is fairly standard. We don't have publicly those grids available, so you still have to use the software that people have written for this. So it's not you can't just these things we calculated ourselves, but using their tools basically. Now, once you start plotting things, so this is different energies as a function of momentum. You start seeing at very high momentum, the deviations start to be very large. And this is potentially problematic because some of the dark matter scattering rate lives over here. And so we believe that the reason for this discrepancy is that in this method over here, this computational method, you assume that all the inner shell electrons are bound into the core. So you don't solve for the wave functions, only for the valence electrons. And so now we're working with a new code that solves for the wave functions of all the electrons. And we believe that that's going to bring this curve more in agreement with the yellow one. Because in higher and higher momentum transfer, you're going to see more and more electrons. And if you don't calculate those, you can't see them. So we need a different.
Why do you think the Merman thing should be the more accurate one?
I don't think it should be, but I can tell you that from preliminary results, running this code is astonishingly close, the new ones. And at the moment, I don't understand why.
Because it sounds like a totally phenomenological fit from
It is a total phenomenological fit that's extrapolated well beyond what you think it should work. However, and again, I don't understand why it works yet. However, there are some rules. This thing, because it has to satisfy things like unitarity, it satisfies a bunch of sum rules. And so those sum rules do constrain what it can do here at high momentum as opposed to low momentum. And so maybe those things are more powerful than I thought they were, and that's why it works, but we don't yet understand. But that's work in progress with one of my
You have a few minutes.
Okay,
You have 5.
well, we'll wrap this up.
Yeah.
I'm almost done. So this is the difference I told you earlier. If you don't include screening, this is what you get, and this is what you get if you include screening. So it's about a factor of a few that we are finding that the rate is smaller compared to the calculations that Reuven and company did in 2015. And so that's not an enormous deal, but relevant enough that you want to know that for the experiments.
You could just turn off the screening, right? I mean,
Yeah, we have a
and so then do you agree with them?
Yes.
You do agree
Very,
with them.
very high precision, actually, much better than I was expecting. Okay, this is the same thing. This is just the agreement between the two different methods, and this disagreement over here we think is because of this effect I just discussed. I will work on this. So the final thing, and again, I'm not going to talk about this in any detail at all, which I think is very cool, is what you can also have is if you have a nuclear recoil, your dark matter interacts with nuclei, and nucleus is kicked out, but it creates an electrostatic perturbation that kicks out an electron from either from its shell, if you're an atom, or from the valence band to the conduction band. And so this has been calculated in atoms for a long while by many different groups, but I think we were the first one to calculate this in crystals. In crystals, it's a bit more complicated because these electrons are delocalized, so they fill all the neighboring atoms, and so you can't just work in a single atom approximation, which people have been doing before. But again, using this energy loss function, this is essentially what we're doing. You recoil the nucleus, and essentially this is final state radiation, where you create a plus and minus pair, effectively, if you want to take a collider analogy. This process over here, again, is just determined by this energy loss function that we talked about earlier. This is the formula. It's a huge mess. Well, it's a very large phase space, obviously, so you basically either Monte Carlo this, or you make some assumptions like isotropy and so forth, some form factors. But basically all the electronic physics is baked in here, and all the phonon physics is in this form factor, which we can also compute. And when you do that, this is sort of our curves. And so here we run into our system, our uncertainties start blowing up because the way we're modeling this form factor over here, we're making approximations that stop to be valid. A few weeks ago, Rubin and company put out a paper where they fixed this up, and so now there's a full calculation that goes all the way to the juice, basically. And this is nice because this is a way of electron recoil experiments to be very sensitive to nuclear recoils by this indirect signal. Yeah. It works really, really well for a low threshold detector. These are Migdal results for xenon, and the reason is this propagator that's close to being on shell. So this thing is fairly small, it turns out, and so it scales like 1 over omega to the 4th, where omega is a typical energy threshold of your detector. So even if you have a small detector that has a low threshold, you get this massive enhancement in the rate, which is very nice. All right, and with that, I'll just wrap up. So we don't want people to do all of this stuff themselves. So we have a public software package called Dart Health, which you can find over here. Written in Python 3, which does all these things. Has lots of examples and a whole bunch of materials. Here are I talked about this, I talked about this, I talked about this. So these are 3 calculations that are included in this package. And we also do absorption and just regular phonon scattering as well. All right, and so with that we wrap up. So like billiard ball is no longer good. You need to account for the fact that stuff is complicated in the real world once you get to long wavelengths. And we've gotten pretty good at this at the moment. I think we have the dark matter phonon scattering pretty well under control to all orders now since this year. And electron scattering, we're almost there. Once we fix up this issue of the semi-core electrons, I think we're also in a very good spot there. And we were able to do a Migdal effect for the first time. Some stuff we want to do is this I mentioned, the semi-core electrons. There's some backgrounds that we want to calculate, something called Frankel pair recombination if you're interested. Some of our postdocs are suffering on that with me. And then the Linhart theory, and there's a few other things that we want to be doing, like spin-dependent scattering is something that we can also do at this point. But that's for another day.
I didn't understand your comment about the delocalization of electrons in semiconductors.
Right.
Metals electrons are delocalized,
Yes.
and insulators.
The semiconductor is somewhere between a metal and at higher energies it behaves like a metal, right? So yeah, so for an insulator you're right. Although even then, yeah, they're not fully, there's still hybridization, all sorts of things. But yeah, a semiconductor, for all intents and purposes, as far as dark matter is concerned, you can think of it as a metal. But the fact that it has a band gap is extremely useful because that means that it's there's less screening going on. So this is the main difference between metals. And so people have proposed like superconducting aluminum, for instance, as a dark matter detector. But it's actually rather bad. Well, okay, it's not super bad. I mean, like here, it doesn't have a band gap. So in principle, if you have a very fancy readout, you can go to as low energy as low dark matter model as you want. Well, this is limited by the band gap of your semiconductor. That's where this cuts off. But you see over here, it's much weaker in this regime. And the reason is that your dielectric function is really large. And so you have, the real part is really large. So you get a lot of screening, and that suppresses the rate a lot. There are a lot of experimental problems by going here, so we're plotting this for completeness. But there's not really, I'm not aware there's a lot of effort going on in trying to do this at the moment, because it's just not an optimal material experimentally. You get lots of dark counts, and it's very, very filthy.
So I'm confused. You're saying you have screen cross section become smaller, but in the plot, why screen cross section is larger than unscreened cross section?
Oh,
am I missing something?
This is a very confusing plot for if you're not following direct. This is just a stupid way we plot things in this community. It's really irritating. So what I mean here is, for a given exposure and a given number of events, this is the fundamental cross section that you could be.
Ah, you can probing. Okay, this.
Yeah, yeah, yeah. So
Okay.
it's not a projected limit because we don't know the backgrounds and the
Mm.
signal efficiency. But if this is the projected limit and the limit where there's no background and
Okay,
help
got
signal.
it. Got it.
That's what.
Yeah, that's why squint is I think is worse than unsquint.
Yes.
Yeah, that's the interpretation.
Well, this is just, yeah, I mean, at some point we started plotting things like this as a community, and now, of course, if you want to be able to compare with each other, it's easier to keep
Oh,
doing
sure,
it.
sure, sure.
But it's incredibly confusing because it looks like a projected limit, and people give me crap about this all the time.
Mhm.
I don't think we will actually probe these cross sections. This is not possible.
Okay,
This is just, it's just a benchmark that we chose to compare calculations.
okay, got it.
For the left hand, you didn't count the screen the result for the
For this one over here,
Huh.
because it's here.
Okay.
That's what I was saying. So like the screening factor for aluminum, especially at low frequencies, is 1,000, and it shows up squared. So it's like 6 orders of magnitude. So that would be right here. And so yeah, we did plot it at first, and then we were like, well, this is useless. So it's and here it's you see there is a large difference. It's not quite as bad because it's a massive mediator rather than a massless mediator. So there's some momentum dependence in the rate basically that's baked in here, which I didn't fully explain.
It's massive. Okay, does the massive matter or does it show the typical
It just means that the mass of the mediator is large compared to the typical momentum transfer, and here it's small compared to the typical momentum transfer. But other than those two qualitative limits, like it doesn't matter what the mass actually is. Of course, it affects what the actual through cross section is, right? But in terms of kinematics, once it's sort of these are the two limiting cases in some ways, and we can interpolate, of course, between them as far as kinematics is concerned. Yeah.
Okay.
So to get the kinds of cross sections that you think you may be able to probe, do you typically need things like light mediators and things like that? I mean, are these large cross sections compared? I think you said this at the beginning, but these are relatively large cross sections compared to, the standard model with some stuff, TeV suppressed operators.
Yes.
This is these cross sections are much larger than that. Is that correct?
Yeah, they're quite a bit larger, yeah.
So you need some light mediators or some dimensionless coupling.
That's right. So there's usually the sort of typical benchmark model people like to use is like a dark photon,
Yeah.
which you can either have it like in the sort of 100 MeV to GeV range,
Yeah.
in which case it would be a massive mediator case, or you can take it to be extremely light but extremely weakly coupled, and then you're sort of in this region.
Okay.
And both of these things work. So for instance, this plot that I poorly explained. So this is with a very light dark photon mediator, so very, very light, low mass. In order to live on this line over here, you're talking about an effective charge of like 10 to the minus 11 or so. So like still very, very small couplings. It's just that like you
Yeah.
get a huge enhancement because of the Rutherford cross section. So you have very, very low momentum cutoff. So there is this enhancement in the scattering process.
So I believe in all the cases you're calculating, you assume dark matter scalar, right?
No, it doesn't matter. It doesn't
But
really matter. There's only one factor.
Its mass cannot, if it's a fermion, its mass should be larger than MeV, right? This is, you cannot have,
No,
I think so. I think that is the minimum requirement on the mass of the dark matter, if dark matter fermion.
Is around a couple EV, I thought.
Couple
That's what
EV?
you're talking about. Yeah, I think so. I mean, this is stronger.
Or KeV.
EV.
No,
I thought
EV.
EV, but not.
Because that's a 10 to minus 3 velocity suppression.
Oh, that's the. Are you talking about the Tremaine gun bound where you try to pack?
I'm trying to say if dark matter is a fermion, there is a minimum bound on the dark matter mass.
Yeah, that comes from like how much dark matter you can pack in a dwarf. And I think that's of the order of an EV.
Oh, EV? Okay,
if I
okay.
remember well. This is, here you start running into the warm dark matter limit first.
Okay, warm dark matter, okay, it's KeV. Okay, I got it.
Yeah, that's
Okay.
KV. So yeah, this is like, we didn't plot the warm dark matter limit because it's basically the same as the stellar cooling bounds. So
Okay.
roughly around a few
Okay, I got it.
And then it's a bit model dependent, but it's sort of in that range.
It can be scalar or fermion, yeah. That's nothing.
This can be scalar from.
Yeah, okay.
Now, whether the mediator is a scalar or fermion or a fermion mediator doesn't, I don't think there's a model. It matters a lot, and we can discuss that if you're interested. Like a scalar mediator is much more constrained than a vector mediator.
Okay.
For various reasons that have to do with screening and stars and all sorts of stuff. That's why we usually take the dark photon. It's the least constrained case.
Thank you. So any more questions? Let's thank the speaker again. Thank you.